Hi, Johannes. Good morning.
Good morning.
Hi, everyone. We'll be starting shortly. Just waiting for a few more people to join, maybe in 5 minutes at 11:05 EAT. So hello everyone, I think we'll just start as we wait for more people to join. So I hope you're well wherever you are, and welcome back to day 2 of the RCMRD GIS and Africa Wetlands Monitoring Webinar on harnessing Earth observation for wetlands, a deep dive into Dunia platform. So my name is Grace Akoth, a GIS analyst at RCMRD, and on behalf of RCMRD and the GIS and Africa program and our partners at Dunia, I'd like to thank you all for joining us today again for an exciting session. So yesterday we learned, we had a strong foundation and we had a great introduction into what Dunia platform entails from Johannes, and then we explored what the platform is, looked at its key features, and saw how it can be used to analyze datasets for wetlands monitoring and other applications like flood monitoring, etc. So this gave us a clear picture of the potential of Earth observation tools in supporting wetland conservation, among other applications. So today, which is day 2, we'll be diving deeper into practical applications of what Dunia platforms can be used and how they can be applied, how the datasets can be analyzed and applied for wetlands monitoring. We'll assess how the platform functions and then explore its potential integration into decision making, probably policy frameworks, and how we can use this information to better monitor our wetlands. So just like yesterday, I encourage you to stay engaged, ask questions through the chat, use the Q&A section, and even you can raise your hands if you have any questions. So with that, I'd like to welcome Johannes and to welcome today's speaker. Over to you, Johannes.
Thank you so much. I'm Grace. Good morning, everyone. Also a warm welcome from my side, from Dunia's side, to the second day of this great webinar. Today, it's not just gonna be me who is talking, but also Cornelia Züger from DLR, from the German Aerospace Research Center, which is with me. And she is going to present a pretty nice example on how to utilize Sentinel-1 data for wetland detection. Since we had a tiny poll yesterday of to get to know each other, and we learned that I guess about 50% of you are more into GIS than into Python, I would ask Cornelia to try to keep her presentation to 1 to 1.5 hours to give me a bit of time to show you a little example on the SNAP software in the desktop environment as well. So we will have basically 2 examples. If we see that this first presentation takes a bit longer than expected, I will also hand you then over this example of mine in the SNAP software, so you can work it out yourself afterwards. And you are always welcome to ask questions, not just today, but also after this webinar, either by using our support, writing a ticket, or you can just simply write us an email if you have our email address. So with this, I would do a tiny introduction first. I think everyone should see my screen, right? You should see the Dunia homepage. Is that correct, Grace?
Yes, you can see your screen.
Great. Okay, so first of all, I would ask you to all sign in. For those of you who actually want to work with us on this example notebook, so on the top right corner, you can click sign in, and afterwards you should see your initials as I currently see it. Don't want to log out because I have some example prepared already. And after you have signed in, I would ask you to click the link that I am going to share into the chat right now. I think it's the more easier approach than the one I showed you yesterday. This link will synchronize the sandbox example notebooks. If you have done so already yesterday, please do it again, because I uploaded the new example notebooks from Cornelia. And after you have clicked that JHub Sandbox EU Africa link in the chat, you should be able to see certain examples in your notebook, and I'm showing you where you should see it. So on the left side, after synchronizing these example notebooks, you should see that directory called Dunia Sandbox Notebooks, as I explained yesterday. And also for you, Cornelia, the example that we're going to present today will be found or can be found in the directory webinar, and then in the subdirectory wetlands. In there, we will find two notebooks. One is called training or tasks, and one is called solution. And how you are going to use these notebooks and explaining these notebooks in more detail is going to be done by Cornelia. So thank you for listening, and Cornelia, I'm handing over to you now.
Okay, thank you very much also for the nice introduction, Johannes. Hello, everyone. Maybe one more thing to add about me. I'm not a wetland expert. My background is more in geoinformatics. So if you have anything to add content-wise as well, just feel free to add it in the chat, or like let me know. Yeah, just as a small disclaimer. Yeah, apart from that, it has been mentioned multiple times. If you have any questions, just let me know, and we'll solve them. I'll try to do it in 1 hour. Johannes, I think that should not be an issue, and then you have enough time to do some GIS examples as well. Do you think it makes sense that I just share my screen and then we can run the notebook together? Yes. On my computer? Okay, perfect. I think it's this button. You should see. Yeah, perfect. Okay, nice. Maybe I zoom in a little because it might be a little bit too small. Is it good like that?
Maybe a bit more. But I think also if you collapse the left side, we should see it better as well.
Can I really collapse it?
I think if you press the directory icon on the left side.
Perfect. Okay.
Yes.
Maybe like that. Okay. Yeah, this notebook has the title Sentinel 1 based wetland change detection. So it is about the detection of wetland based on a radar satellite by Copernicus, which is called Sentinel 1. Of course, I called it now wetland change detection. However, what it basically does, or what we'll be doing in that notebook, is more water detection based on thresholding, but you see that later on. We'll not only detect the water area, but we'll also have a look at how it changes over time. That's also something we can do. Yeah, as with every Jupyter notebook in general, we're starting by just importing the packages that we need for the following workflow. Python packages work like predefined functions, maybe you could say it like that, and then we don't have to implement them ourselves. We're just using them by importing the package, and then we can use the function directly. Maybe, as I don't know how experienced you are with these notebooks, you run a cell by activating it. You just click on it, and then you click on this run button on the upper left. And by this, it just runs the cell, as you see here. And then it automatically goes to the next cell, so then you can run that afterwards. And that's what we'll be doing for the first 2 cells. So we are just activating the packages that we'll be needing in the following part of the notebook. Yeah, and then after we've done that, we can really start with the content of the notebook or the actual workflow. So when we want to detect wetlands or wetland change, of course, one thing that we need to do at first is to decide which area we're actually interested in. In this case, I just kind of randomly decided for one, which is a river delta in Kenya, the Tana River Delta. This is quite an important, vital ecosystem in Eastern Africa, and it is also recognized as a wetland of high international importance, and therefore it is protected under this Ramsar Convention. So yeah, that's the reason why I decided to take this one as an example. Of course, if you are particularly interested in a specific type of wetland or in a specific wetland, then of course feel free to change the AOI later on. Maybe you can do it later, maybe tomorrow. Just for this workflow right now, I'll stick with that particular AOI. It is not a big effort to change it. So if you feel brave, just try it out later. So apart from the AOI itself, which in my case is a polygon, I just defined a rectangle with certain coordinates which cover my area of interest. I also need to define a start and an end date, just a time range, which covers like a particular event, for example. For me, it was just 1 year. I just thought, okay, let's take the year 2024. And I'm now interested in changes that happened during that year, basically. Yeah, and then what we're doing is now that we're inserting this information, so the geometry of our area of interest, the start date and the end date, we are inserting this information into a function. This function is part of the EODAG package. This is what we're doing here. So we're loading this package, and then we are working with the function search that is part of this package. And we're inserting basically the search criteria. So what this package does is it lists all the files that are matching our search criteria. So we are selecting a provider. And then what we're doing is we say, okay, we're interested in Sentinel-1 GRD imagery in a certain area, which is our AOI, from our start date until our end date. So these are the search criteria, and then we can run the cell. This does nothing. So it seems like it does nothing. Of course, it does something. Because now we stored the results of our search in this variable here. So it's called search results as 1. And in this cell below, we run this cell now by clicking on this button again. We now get the list. So this is the list, which is provided by our EODAG package, which shows all the images that are matching our search criteria. By the way, please just let me know if I'm too fast or too slow. I can adjust that, of course. Just give me feedback if you think I'm too fast, or if it's too boring and I should hurry up. That's of course also fine. So this list of Sentinel-1 images is the list of images that are covering our AOI during our time of interest. As you saw, we are specifically now looking for Sentinel-1 GRD imagery. The issue with GRD imagery is that it's usually not auto-rectified. However, if you want to do a time series analysis, it is quite important that the imagery is auto-rectified, because only then you can be sure that a pixel is like a certain pixel is always at the same location. And that is, of course, crucial if you want to detect changes in a certain pixel. So it has to always be at the same location. And that is the reason why we're not using the GRD imagery for our analysis, but we're using the radiometric terrain corrected imagery, which is called RTC, because they are auto-rectified and can easily be used for time series analysis. And now comes a rather tricky part, because now, based on this list here, we need to find the radiometric terrain corrected imagery in the Dunia data browser. And here, yeah, I kind of made that as a small task for you. So I would like you now to actually find the data in the data browser that we need. So for this, you have 3 hints that actually, I think, make it feasible to do that. So the first one is that all the data in the Dunia platform can be found in the EO data directory, which is like on the first level of folders. This is the EO data directory that I'm talking about. So if you double click on that, maybe it takes a minute. Yeah, okay. You see a lot of folders in here. And you also, okay, that's now a big hint. You also see a Sentinel-1 RTC folder. And then the second hint is that we are interested now in one image from the 9th of January 2024. And we also, by defining our AOI, we already know the approximate location of it, of course, which is, in our case, 3 degrees south and 40 degrees east. And this is all the information you need now to find the data in the data browser. And I think I would give you a few minutes, maybe 3 to 5 minutes, to find the location. And maybe if you found it, if you found the files, just indicate it in the chat, maybe by a thumbs up or something, and then I know we can continue. Okay, so see us in 3 minutes, I guess. Okay, so I saw one thumbs up by Johannes. I hope that it worked for all of you to find the data. I think we'll just continue, and if it did not work for you, you'll get the, yeah, okay, perfect. You'll get the link in the following section anyways, so it should be fine, I guess. Okay, so perfect. Yeah. Okay. So what you found, or what you should have found, is actually a folder that contained some files, I think 6 or 7, and 2 of them should have these names here. Let me collapse that again. These names here. So you have 2 image files, 2 TIFF files. One has the ending VH, and the other one has the ending VV. These file endings indicate some information about the image file. I think I might quickly get through this here, and then I think you'll have a better understanding what these abbreviations mean. So with Sentinel-1 data, Sentinel-1 data is quite different to like other remote sensing data, because like, yeah, you differentiate radar data basically from optical data. Optical imagery, optical satellite imagery is basically like images that you could also take with your phone or your camera, which is just capturing radiation that comes from the sun and then is reflected by the Earth, by the Earth's surface, and then that is what's captured, for example, by satellites like Sentinel-2. Which are optical satellites. And then you have another type of satellite, which is radar satellites. And the special thing about radar satellites is that they are actually emitting microwave radiation themselves, and then measuring what's actually coming back from the Earth. And here, what really matters is the type of surface that is hit by the radiation, because depending on the object that is hit, the radiation is scattered in different ways. And I wrote down here 3 different types of backscatter that are maybe the most important ones. The first one is surface scattering. That is what's happening when the radiation, the radar waves, are hitting a very flat, plain surface. Because what's happening then is, if you see my mouse, I can just show you quickly. So if here on top, if that is the satellite, and then the radiation comes down to the Earth and then is reflected back, you see then it would be reflected like this, so in a rectangle. And that means that the reflection actually is going away from the sensor, resulting in a very, very low backscatter. So basically nothing is measured at the sensor because everything was reflected the other way. And then, of course, what is also happening if radiation is hitting a building, for example, there you sometimes have the effect of a double bounce, which means that, as the name says, the reflection is not, the radiation is not reflected once, but twice. And this, you see that here, this would then result like in the radiation being reflected exactly in the same direction as the sensor. And this, of course, then results in a very, very high backscatter value. So you have a lot of radiation going back to the sensor. And then the last main scattering type, maybe you could say it like that, is the volume scattering, where the radiation comes to an object and then is scattered in that object. This, for example, happens in trees a lot or in vegetation in general. So the radiation is scattered within the object and then somehow comes back out of it. And this can result in very high or moderate backscatter values. That kind of depends on the objects individually. So these are the 3 backscatter types. And then What is also differentiated in radar imagery is the polarization of the image. And that is actually what this abbreviation means. So VV is one type of polarization and VH is another type of polarization. Polarization means or is the direction in which the radar wave itself vibrates. So radar waves vibrate or can vibrate in different directions. And the V stands for vertical, which means the radar wave is vibrating in vertical direction, and H means it is vibrating in horizontal direction. So if you have a VV polarization, it means that the radar satellite itself is emitting vertical vibrating radiation and is measuring the amount of vertical vibrating radiation that comes back to the sensor. And VH means that it's emitting vertical vibrating radiation, but is measuring the horizontal waving radiation that is coming back. What does that mean? It basically means that, and that to me, that is kind of like intuitive as well, because for example, if you have radar waves going into a tree or bush, it's really like going around a lot. Oh, perfect. Yeah, thanks for the visualization, Johannes. So in the chat, you really see a good example of like what I tried to explain. It's the image of vertical and horizontal vibrating radiation. And if you have a vertical vibrating radiation going into a tree, it's really scattered around. Like you have this volume scattering. It's really messy. It's going up and down. And then, of course, possibly it can result in the radiation vibrating back in horizontal direction. So this means, and that's also what's written down here, the VH polarization is very sensitive to volume scattering. So if you have a VH polarization, you can expect comparatively high backscatter values in areas where volume scattering happens. So, for example, above forests, or also above agricultural sites if there are crops on the fields. And then on the other hand, VV, the vertical polarization, this is often stronger over flat surfaces. So here you have higher values, for example, above the ocean. So this is just a small excursion about that. Going back to these data sets or to the two images, now you maybe better understand what that means. So in our AUI, in this one particular image in that time, we have these two polarizations that are available for our image. And in the following, we want to actually just visualize these two images to see maybe their difference, if they're actually different, if we can see something like that. And we are doing that by inserting the image path into the cell. And now just for convenience, I think I will, or actually you can do that yourself. You now have the solution notebook as well. So now that would be the time to go there and just copy and paste this cell with the results into our cell. So this is the result. I can also copy that into the chat. And this is now what should go here. So we now insert the paths to our images into this rasterio.open function. This function, as you would maybe guess, opens the TIFF file, and yeah, we can then visualize it later. So after inserting the respective paths in there, we run the cell. Oh no, now we have an error. What's the issue? Oh, it says no such file or directory. Let's see what the issue is. SAR, RTC.
It's probably because you need to add home EU Africa in the beginning of
Oh,
that
okay.
chart.
Yeah, true. Because now I started the notebook from a different location compared to when I tested it. What is it called? Home, EU Africa, and then EU data?
Yes, exactly.
Okay, perfect. Let's try that. Okay, now it just has an issue with the function, but that's maybe just my fault. Yeah, because it restarted the notebook now. Okay. Okay, so now it's loading the image files. I just copy the corrected version in here as well. So after inserting these paths, you now have stored the image data in these two variables. So as one underscore VV underscore data and underscore VH underscore data. These are our two variables with the data in there. And now we want to visualize it. We just do it by using a very simple function, which is called plt.show. But before we can visualize it, what we're doing here is we are converting the values in the data set to decibel. Right now, it is in linear intensity values. However, it kind of makes sense to just convert it because then the data gets, like the values get a little smaller and they're more handleable. And also, it is kind of the data range that the value should be in. So we're just converting it. And we're doing that by using a log function. We're applying a log function to the intensity value, and then we're also adding a very, very small number just to be sure that we're not dividing by 0 at some point. Yeah, and then we can easily visualize it by using this plt show function. Here we are first defining the data set that we want to insert or that we want to visualize, and then we're defining a color map, a C map. In our case, I just chose gray. Of course, you can also choose blues or reds. In this case, it's grays. And then we are also defining a value range in which the color should be scaled so that we see as much as possible in our case. Or in the case of these Sentinel-1 data sets in decibel -25 to 0, almost always is working somehow. If you don't see anything, then maybe adjust it a little, but in this case, it's working quite nicely. And yeah, then you can run the cell and then you see the image again. So it's working, it's running. Yeah, now we see a nice image of the coastline of Kenya, or one part of the coastline, and then you also already see like the area where the river delta is located. This is the VV image, so the VV polarization, which is more sensitive to water, and we see that the water appears to be quite bright. It is not very bright, but it is somehow bright. And now if we visualize the VH image by running the run button, you now see that in the VH image, the ocean appears to be very, very dark. So here we obviously have quite lower reflection values over the water, which is in line with what we read earlier. So we heard that VV is quite sensitive to water and VH is more sensitive to volume scattering, and that is matching with our outcome here. So that's good. And then as a next step, I also included another option that you could apply to the data, which is basically computing different indices or combinations out of these two images. For example, you could subtract them. That's what I tried here. So I just took the VV data and the VH data, subtracted them, and then converted them to decibel. And then visualize them, and then that's what the result looks like. So yeah, just to show you that that is also an option. In the following, we will work with the VH polarization, as this image here seems to have the biggest difference between ocean area and land surface area, and that's actually what we want. I mean, of course, we're not particularly interested in ocean, but we are interested in water areas, and in this image here, the water seems to be quite easily distinguishable from land surface areas, so that is the image we will continue working with. As I think I should be as fast as possible, I think we'll skip this bonus task. Of course, if you later on are still keen to try it out, feel free to do so. You have the solution in the other notebook. So yeah, you can do it later, of course. We don't need it for the workflow anyways, so I think I'll just skip it. This would be a task to try to divide two images and then see how that looks like. Okay, as a next step, we are deleting some images. Of course, this one is not computed yet, so we only run these two. Okay. Maybe it's not necessary anyways. I think we have enough memory space. So I'm not sure why that is not recognized. Okay, anyways, so after now having a look at these images, at these Sentinel-1 images, there's another step which is quite common when working with Sentinel or with radar imagery in general, which is speckle filtering. So radar images often have this speckle effect. I think it's sometimes also called salt and pepper or something. So you really have like a speckly image that has a lot of like small dots and noise in there. Which is normal. That's just part of how these images are, and one effect of, or like one side effect of their acquisition. But there are ways to deal with it, and one of them is to apply this enhanced Lee filter. So there are also other filters, enhanced Lee filters, one of the more common ones, I would say. And this is now a quite, more complex function with a lot of different ways of filtering depending on how much the values are deviating from each other in a small area. So that is more complex. I think we won't go into further detail with that, but we can of course always apply the function because it's already defined. So we are just running this cell here where the function is defined, the ELF underscore filter function. So we are running this. And then after we run that, we can apply the function, which is also quite easy because we just have to insert the file path again. Of course, this is now wrong as well. So we have to add home underscore EO Africa. We have to do it like that. I also copy that into the chat, so you can just copy and paste it into your notebook. Here we are really just inserting the file path to our VH image into the ELF underscore filter function, and then our image is filtered. Very easy, right? So it also does not take a lot of time, so that's quite nice. And then now we might also want to see the effect of the filter, because like in theory it should have an effect, but of course we can never be sure. So if we run the next 2 cells, you can have a good detailed view of a small extent of the image to really see the effect of the filter. And in my opinion, it is quite nicely visible, because in the first image, this is the one that is not filtered at all, you really see the speckle effect that I was talking about, right? So it's like there are a lot of darker dots and you have brighter dots, and it's really like this salt and pepper effect. And then after filtering, of course, it now looks more blurry, but you clearly see an effect, and you see that maybe it's less speckly. However, of course, it's now somehow more blurry. That is always a trade-off, of course. But we see an effect, so the filter might have worked, which is nice. Yeah, and then continuing, now that we filtered it, we can finally run a water non-water classification, which is like the main point of this notebook, to really distinguish water areas from non-water areas. This is quite a straightforward process, as it's a binary classification. So we only have these 2 classes, meaning that we can apply a threshold on the data. So we can see, okay, we define an value x, and every pixel that has a value above x is part of class A, and every value that is below x is part of class B, for example. And that's what we're doing. So we want to define a threshold, and every pixel that has a value higher than this threshold is water, or no, is land surface area, I think. Yeah. And every pixel that has a value that is lower than x is then defined as water area. This is somehow a trial and error process, honestly, because there's not like a fixed predefined value where you know, okay, this is the perfect threshold value for water detection. That's, to my knowledge, not the case. So depending on the image area, on the image or the area, you really have to figure out what's the optimal threshold. In this case, for this image, for this area, I figured out that -18 dB seems to be quite suitable, because it really is the value where you can quite nicely distinguish water from non-water. So I tried out and decided I'll take the -18 as a threshold, and then true, yeah, okay. So there are, Johannes wrote it in the chat, there are indeed automatic approaches to do so. So in case you have a lot of images where you kind of want to optimize the thresholding, maybe have a look at the Otsu thresholding methods, or k-means. You said, okay, yeah. So that's right, there are approaches. I didn't use them, I just tried out, because we only have one image in this case. So it is also possible for 1 or 2 images to just try out. If you have more, maybe have a look at these methods. -18 was our threshold, so I just applied this value as a filter value. This is what I did here. So we have the our image. It is called VH filter DB because we have the VH image that was chosen. We applied the leaf filter on that. That's why it's called filtered. And then we converted it to decibel. So it's VH filtered dB. And now we are just typing greater or bigger than -18. That is all we need. With this formula here, Python is automatically checking every pixel and is applying the -18 check on it. And then in case it is true, so in case the pixel is larger than -18, it applies a 1 to the pixel. And if it's false, so if the image is smaller than -18, then it applies a 0 to the pixel. Assigns a 0 to the pixel. And that is all that's done. And after doing that, this small command here, we already have a binary classification. Of course, as before, we can visualize that binary classification by running this plt.imshow and plt.show functions. In this case, I did not choose the CMap gray, but CMap viridis, which is, I think it's like a color bar from yellow to purple, and then like the values in between. So as we only have the value 0 and 1, it is yellow or purple. And you really see that it kind of seemed to work. So this value of -18 seems to be quite suitable. We can, of course, clearly distinguish the ocean, but we can also really see the delta areas quite nicely. And also some smaller lakes and stuff like that. So it is. It seems to be quite suitable. That was the first main part of this notebook. So we now imported an image and we filtered it and we ran a threshold on it, and now we have a binary classification. Of course, if you want to run a change detection, you at least need one other image, the second one. And that is now the second part of this notebook. So what we're doing now is we're just selecting a second image, running a filter on that, and then we are comparing these two images with each other. So we are now selecting another image, which is the number 15 out of our search results as one list. You remember that? This was this list here, where we filtered the Sentinel-1 imagery using the EODAC package. And now in the first round, we took the first image, which was the one from 9th of January. And now we take the number 15, which is the one from, I think the 19th of July, maybe. Let's see. Yeah, 19th of July. So that is the number 15 out of our list. This time you don't have to look for it again. I already copied it in here. Of course, the paths now are not complete. I'm very sorry for that. That's kind of annoying. This is what it should look like. You just have to add home EO Africa to the path here. This is what the cell should look like. We already know we want to use the VH polarization, so that's the only one we want to open right now. So we use the rasterio.open function for the VH image from the 19th of July 2024. And we are opening this one by running the run command. And then again, we can visualize it. That's quite straightforward now, as we've already done that before with the other image. You see that it's really nicely, like the water is very, very dark and the land surface area is more bright. So it is really a good choice here to use the VH image. And then, as previously done, we can run the speckle filter again on this data. And then apply a threshold to it. So this is then the corrected cell for the speckle filtering. So it is speckle filter converting to dB and then thresholding. and then plotting. So we are directly plotting it in that cell as well. And now you see you have a second image. It looks quite similar to the other one. It might be not, though. We cannot be sure, of course, because it's quite zoomed out. It is more an overview map, not really detailed by now. And of course, the general pattern seems to be the same, but there might be changes. We have a time gap of 7 months. So yeah, we assume there'll be changes. We just cannot be sure right now. So the next step now in the workflow is to do a change analysis. This, of course, it can be done in different ways. I chose a rather simple one here, which is just dividing the two images by each other. And this is now another task that I would like you to do, because you have these two classes, water as 0 and non-water pixels with a value of 1. And if you subtract two images from each other, of course, you expect certain type of values to appear. And of course, that's not a really complex task. It's just like good to think about it and to really see what would you expect each pixel cell to be after the subtraction. So you see here there are 4 different scenarios. We have the scenario water pixel in the first image and then water pixel in the second image. If you divide them from each other, what would be the result? Same for non-water to non-water, and then we have water to non-water and non-water to water. These are the 4 scenarios, and I would like you to maybe just think about it for 1 or 2 minutes, what the results then are in the subtraction image. Okay, I don't think we need to wait a lot longer for that, as it's not a really complex division task. So we have the results then would be, I think, water minus water is 0, as we have 0 minus 0 is 0. 1 minus 1 is 0. Then we have 0 minus 1, which is minus 1. And we have 1 minus 0, which is 1. Okay, so these are the 4 resulting values, or three resulting values that we expect in our final image after dividing one time step from another one. And this is what we're doing in the next cell, actually. So we are computing a binary diff, I call this image, which is computed by dividing minus 15 from by dividing the binary 15 image from the binary image. So we divide, subtract the time step 15 from the time step 0, basically. And then what is done here is just defining a data type. So we say that we want to have integer values. And then we are plotting. We are plotting the resulting image. And this is what it looks like. What do you see here? Not a lot, actually, right? So we have this green background, which has the value of 0, which means, like, of course, in the large proportion of the image, nothing changes. But then we have a few patches with a value of -1, and we have a few patches with a value of 1. Okay, so we know that in some areas it changed from water to non-water, and in others it changed from non-water to water areas. But like I said, it's not really that you see a lot here. We don't have a background map. It is quite zoomed out still. So in the next step, we are zooming in a little and hopefully see a little bit more detailed information about the area and its changes. Of course, in these binary classification images, it's still hard to figure what changed in the two time steps. Maybe a little bit. You see it here in the upper image. There's a lot of water area in this area here, and here it's a little less. And here there seems to be something new that was not here in the first place. However, it seems to be quite similar. But then if we're zooming into the difference image, we really see where it changed. So we see here these newly appeared water areas, and we also see some water areas that were gone. We also see that there might be like some clustering maybe. So here we have an area where a lot of water just disappeared somehow. And then we also have areas where there was new water appearing. However, just to get an even better overview, in the next step, I also added a background image. So we just added one of the satellite images as a simple background to just really see where the ocean is and where the rivers are, because right now you don't really get the context, right? So this is now the better version, I would say, of the difference image. So you really see that close to the river areas, there were a lot of changes. So in the delta itself, we have this area where water areas disappeared. And then we have these areas here close to the river arms where new water area appeared. So maybe it got wider a little. Yeah, and this is basically already all that is done in this notebook. So it was more like a rather simple approach on how to do a binary classification of water, non-water, and then to see if we can somehow figure out changes between images. I don't know, Johannes, if we still... The slide is a guide much later. Yeah, I think we can provide that as a PDF, right? The notebook itself.
Yes, that can be also provided as a PDF.
Yeah.
I think if you export it, you can save a Jupyter notebook in different formats.
And don't you also maybe, like, can the participants also just download it from Dunia directly from the platform? Is that also possible?
Yes.
Okay.
So if you go to your notebook on the left side, in your file explorer, and of course you can do that with everything. If you do a right click on a notebook, then you will see the option download. Also, if you want to export it in a different format, I'm not sure whether PDF is possible. Let's see, but I know HTML is. If you go to File on the top left corner, you can always specify Save Notebook As. And there you should usually get a few options. Let me see whether can do so.
Here you can do it. Save and export notebook as.
Yeah,
and there you
here
get
we go.
the
And here
options.
you got PDF as well.
Yeah. Okay. For the link to the notebook in Dunia, I think you have to run the link that Johannes sent around in the first place to
Yes.
synchronize with the Git, right?
I can resend it. This link is going to synchronize your environment with the example notebook, so you can use them right away in your environment. In case you want to use them outside, this is also possible. If you want to run them locally, there is also the direct link to the GitHub repository, which I'm posting right now. Yeah, both are basically the first one is synchronizing them and automatically loading them to your environment so that you can execute them right away. And the second one is basically just the repository behind it where all the examples are stored. Whenever we have new examples, of course, you would need to reuse that link and resynchronize. But you see in this Jupyter Hub sandbox that we have some Git versions, so you can also use them to pull the newest changes or even use your own repositories. We have a question. Are these changes able to be converted as shapefiles, just indicating the bounds? For example, new water shapefile. There is the possibility of doing so. So you could again extract or there is a function called raster to vector. You can either do that in GIS, but also with Python, where you basically convert a raster file to a vector file, and therefore all the concatenated or all pixels that form a -1 or a 1 patch, or a patch with a value -1 or value 1, will be separate polygons if you specify the vector type polygon. So there is indeed the option of vectorizing that result. And then, of course, it's up to your visualization in QGIS or wherever you want to do that. But the next example is going to be in GIS, because we heard yesterday that a lot of you are doing GIS more than using the plain Python code. But before we start with the second one, I would like to ask you for questions to Cornelia, because I think it's easier if we first answer the questions related to the notebook or to this approach. Okay, so there is a new one. Can you just give the code as HTML file, please? We can do so, of course, as well. Maybe while I'm doing the presentation, Cornelia, you might just export it as a HTML, download it, and put it to the chat. I don't know. Yes, so I will then share my screen for the second example. I think you should see my screen now. Can somebody confirm?
Yes, we can see it.
Okay, great. So I'll close that pretty nice example. Thank you, Cornelia, again for this example. It was really well explained, and that helps me with my example, because then I don't have to explain some of the Sentinel one decisions I made. So yesterday somebody was asking, how do I get the data into my desktop? Of course, in our sandbox in the Jupyter Hub, we can use the EOData mount point, as we just saw with Cornelia's example, but you can also use this EODAC plugin that I showed you yesterday, where you can draw your polygon, define your Sentinel mission, like Sentinel-1 GRD, and so on. Unfortunately, RTC is not included, so this is why we went with the mount approach, and we have the date range. Of course, you can also define some filters like cloud filters in case of Sentinel-2 imagery as well. So this is the way I currently go with. We are using your feedback, however, to create a nice QGIS plugin, so that you can have this kind of feature into integrated to QGIS as well, so that you can get the data visualized even more easy. But for now, let's go with that approach. As I showed you yesterday, let's start with a new cell. I can just easily select my Sentinel-1 GRD, and I will go stay with GRD instead of RTC, and I will choose some date range, and just like that, I can click generate code, and it gives me the code to get my data set. Important to notice is that we actually want the provider QGIS S3 in case we want to point to the data that we already have called EOData. If you don't use this provider, you might not get the path information in the metadata, and then it's difficult to find the data. So this is quite important to mention. So I already did that. Oh, gonna undo that. Okay, I cannot. Very unfortunate. Anyway, I just did that for the 23rd of the 19th of November 2023 for a region that is the Shebelle River Basin. I don't currently have this code here. I think if I use the EODAC library, it's somewhere down there. Anyway, after you get these search results, you can just get the path to your file by taking one of these search results. Let me just quickly, so you will see the search results like that. In my case, I just have one search result because I searched for 4 days, and that's the 19th of November 2023. Now we see we can even explore that item here. Every item in this search results variable has properties. And if I click the properties, I see all the metadata, right? An explanation about Sentinel level 1 ground range detected data. That's what GRD means, and so on. The date, the mission start date, and so on. That's all quite nice, but we don't need that information. The information we need is the product identifier, because that gives us, as you can see, the path inside the EOData directory. So I choose the first element of my search results, use the properties, and then I go for the product identifier. I merge that with my home directory, my root directory, Home EU Africa, and just like that, I get the path to the file of interest. This is a safe directory. This is the format the Sentinel data is stored in. That's totally fine. We don't need to go for a specific file as we did before. We just take the entire directory. Now we know where the directory is. Of course, inside the desktop environment, I could also just go to my home directory, I go to udata, and then I can search for that file. But I am lazy, and that is the reason why I use a symlink. A symlink is basically just a link. I just link this, I just copied this path here, and with this command ln-s home EU-Africa desktop, I just create a link on my desktop. I will just put that into the chat so that you have this example as well, because you can just ignore the rest. You don't have to re-execute it. You can just use that command as well. ln-s is creating the symlink. And what does that mean? If I go to my desktop environment, I now see I have this directory, the Sentinel 1A grdh file, the one I wanted to have. But it is not copied, so I don't need the storage. It is just a link to the EUData directory. And that is way more easy if I start the SNAP software or QGIS to use that file instead of having to search it. And now I want to show you SNAP instead of QGIS. We will use both though, but the huge advantage of SNAP is that it comes with a lot of tools that GIS does not. And some of these tools we already heard today, and that's the radiometric terrain correction, that's a speckle filtering, and so on. So I will open a complete new, can I just, I think I just close it. Nope. And I just reopen it because we do it all together now. Okay, there is an update. Here we go. So we open SNAP now. I will just say no to the latest version. So what I do now is I just drag and drop my Sentinel-1 image in there into the Product Explorer. You see it's loading, and I see the entire saved directory is now here. If I double click it, I get some information. I get the metadata if I want to, and I get the bands. Every satellite data set comes with some bands, and we also saw these bands in our last example from Cornelia. We got the amplitude and we got the intensity of both polarizations, VV and VH. What we want to have is the intensity. The intensity and the amplitude is basically the same. I think one is the square of the other. So we'll just stay with intensity of the vertical. Why? Because as Cornelia explained, this is the polarization we usually want to take if we go for water detection. So if I just double click intensity VV, it will automatically open that image in the image view on the right side. In the beginning, it might take a bit because it's a bit bigger, but let's just wait a second and we'll see. Wow, a lot of noise, a lot of speckles, as we heard before. So let's zoom into an area of interest with some water body to get maybe a better understanding. You see the magnifier glass icon here, that's the zooming tool. And let's just zoom into this area where we see there is some kind of river. Nice, right? That's the Shebelle River. And what we now want to do is, to give you a background, in November 2023, this river was flooded. Of course, we can do change detection, having an image from before and after, as Cornelia did, but you can do that yourself. I just want to show you how you can do some of the steps that Cornelia showed also with the SNAP software. So we just go for the classification of one image now. So first we zoomed in. Now let's do a subset. I don't want to classify the entire image. The entire image is quite big, and I don't need the entire image. I just want my river basin, right? So how can you do that? You can do that by clicking raster up here. And then we have a function or an option called subset, raster subset. And if you click that, it opens up a specified product subset pop-up. It's now loading. You see on the left side, the subset is automatically what I currently see in my screen. And that's totally fine that way. So, yeah, let's just go with OK. And just like that, we have a subset. I can also double click on the left side to collapse one of the folders. Let's open up the new one and visualize the intensity VV of our subset again. So now that we have this new subset, we want to calibrate it. We want to do a radiometric calibration. That is also one of the most important pre-processing steps in working with radar data. So what you do is you have a radar menu. In this radar menu up here, you see a lot of tools that are important. For example, the speckle filtering that we were talking about before, applying an orbit file, which is also very important, and also the radiometric terrain flattening. We just go with that one first. We click radar, then radiometric, and then we click calibrate. There is a lot of options. We're totally fine with all of them, but in the processing parameters, we want to define VV because that's the only information we need. We don't need VH, right? We said before, VV is most powerful for water. Let's go with VV. And the default option of getting the sigma 0 band is also totally fine for us. And it tells me it already exists. Do I want to override it? Okay, I'll just say yes. And just like that, it took 2 seconds. I have my new calibrated subset. Let's check out the subset. Go for bands. Here now I should just see the VV, and that is the difference. So we see there is some calibration. It might be minor, but it's very important as one of the steps that we want to do. So after this radiometric calibration, let's go for the speckle filtering that we did before. As you saw, we can just do radar, speckle filtering, and since we just have a single product, we use a single product speckle filter. And now that's very important because, of course, a multi-temporal speckle filter is more powerful. If you have more images that the speckle filter is using, then it is also better to filter out the noise, right? Because then it sees, okay, if that is this pixel is always the same over all the time slots, then it's probably not noise, but real. If it is always different, it's probably noise. So this is why it can better interpolate and get out and filter out this noise. Since we just have one time frame now, we stay with a single product speckle filter, however. Again, we are totally fine with our results, with our default parameters. Instead of the Lee sigma, I just want to use the Lee filter. You also see the refined Lee filter from that Cornelia used. Let's just use the Lee filter for now. Do I want to override? Yes, let's override again. Another 2 seconds, and I have my filtered result. Again, I can click, go to the bands, and view the change. Wow, that's a bigger difference, right? Instead of a lot of black pixels in between white pixels, I see it a bit more homogeneous in this filtered result. Let's maybe clean up the left side here. Okay, so what did we do so far? We used the Sentinel-1, viewed the Sentinel-1 VV polarization image. We created a subset to really focus on the location that we want to focus on. And then we did some pre-processing. One was the radiometric calibration, and one was the speckle filtering. Of course, as I said, there are some other options for pre-processing, but we will stay with these two for now. Now, similar to the approach of Cornelia, we want to create a binary now. How can we do that? SNAP comes with a pretty nice color manipulation tool. On the top left corner, you see the navigation so that we see where we're going around, uncertainty visualization, the world view to know where we currently are. So we see this is also quite nice because we see where in Africa we currently are. And we have our color manipulation. In the color manipulation, we use the slider. And with the slider, we see the histogram. The histogram is the distribution of all our values. So we see which value appears most often, which one doesn't. I'd like to use this logarithmic view because it gives us a better understanding of filtering. You see, if I don't use that, or whether I use that, it really makes a bigger difference between the water bodies and the rest. And now I can use this threshold slider to really define these differences. So the more I put it towards the lower values, the bigger I see the differences, right? But let's be cautious because I also don't want to filter away important areas. Now here we see one part of the river. If I use the filter here, we see this is somehow grayish, so we might miss that kind of part of the river. If I come here, we see it's getting a bit more, right? So, but I think a value of 4 is probably very much wanted. So if I want to stay with this value 4, let's say we have 4, it's a bit difficult to see, I know. I cannot zoom in, but on the left side, you should see 4.0 E minus 2, right? Of course, you can use other filters, other thresholds. They will then, of course, result in different binary results. So now that we have that this is just for a manual help for us, right? So that we can somehow manually figure out that threshold. Again, as we said before, there are other tools where you can actually use thresholds. I think the Otsu thresholding is also inside the SNAP software. Classification, we have unsupervised classification, we have the k-means cluster for segmentation, image analysis, data conversion. So there are a lot of options, remote sensing tools. Cannot find it right now, but I'm convinced I saw the Otsu filter somewhere. Anyway, let's go and create this binary now from the threshold that we manually figured out. And we can do that with the raster math calculator. So in raster, we go to the band math option, and that's the top one. If you click raster band math, you can define a new name. Let's call it flood. If you want to store it as a file, you can just untick that box. I will keep it virtual because I will also show you how you can export it afterwards as well. And now I need to include my band math. And my band math is the following expression. And I will put that expression also in the chat. It is my sigma 0 VV layer that I currently opened. And I say, if that is smaller than 4e minus 2, then it is a 1, otherwise it is a 0. I normalize that result with 255 to get a 8-bit result. And if I execute that, this is what I get in response. Pretty nice, huh? So I see the difference quite clearly. Of course, there's some dots, some areas besides, but don't forget that Sentinel-1 is not just good for water, but also for wetness detection. So those might be more wet areas. And now we see this flood result is now also part of our bands section in this subset that we have created. Now, if we want to watch that in QGIS, there is one step we need to do, and that is a terrain correction, because without the terrain correction, we will not be really able to put it into the right location. And we actually want to have it in the right location to compare it with some other satellite data. So if I go to the radar menu, where I also see the other pre-processing methods, I can go to geometric. Where is it? Here. And in geometric, you will find the terrain correction. And here we use the range Doppler terrain correction. Again, we are fine with the parameters, but for the processing parameters, we just select the flood because that's more than fine for us. We don't need to use the sigma value. We just want to have the flood. So I'm running that. Takes a bit longer than the steps before. And it's done. Now I have a new 5th subset. If I unfold it, I see I have the flood VH. Don't be confused that it says VH. This is because of the terrain correction. Now, if I want to store that as a file, and we want to do that to be able to visualize it in QGIS, I can just click File, I can click Export, and then I can use whatever format I'm most familiar with. For raster, we mostly use a GeoTIFF. And if I click GeoTIFF, it asks me where I want to store it. Please, it doesn't make sense to store it in the Sentinel folder because that Sentinel folder is write restricted, so you won't be able to write it in there. Just go to your desktop, name it. I named it flood.tiff. So you can name it whatever you want to, but in your desktop or in your private and working environment, please. And then just click Export Product. and it is now exported. Before I hop over to QGIS, again, this tool by ESA is pretty powerful. You see not just vector or raster tools that are familiar to you if you use GIS, like basic raster to vector, band extractor, segmentation, change detection algorithms, but you have specific optical satellite tools. For example, pre-processing, you can use Rayleigh correction, dark object subtraction. There are a lot of pretty nice tools out there. Of course, you need to know them, you need to be familiar with them, but if you are, these ones are really powerful. And I rarely know anyone who does Sentinel-1 pre-processing without the tools provided by the SNAP software, because if you go to Radar, you get them all. You have the orbit file that you need the terrain flattening, you need the speckle filtering, you need the terrain correction, and so on, right? So this one is quite powerful. And if you're familiar with remote sensing and GIS, it shouldn't be a huge difficulty to use it. Now, let's open QGIS. If you click on Applications on the top left corner, on Develop Education, you can then press QGIS and open up QGIS. I have it already open. And I can tell you how to visualize your flood the way I did it here. So usually you get your result like this. If you put it into your QGIS, you have this black and white image that we saw in SNAP. Now I want to remove that black background, and since it's water, I want to visualize it blue. So what you can do, so everyone who is familiar with GIS knows, okay, I just changed the symbology. Instead of a single band gray color, I use a pseudo color. And in the color ramp, as a color ramp, I can choose the blue color ramp. So usually it gives you some, here we go. Here it gives you some options. You can use the blues, the greens, and so on. I chose the blues because it makes most sense. The rest is basically an automatic classification based on the histogram. But if I do that, you see I still get this slight blue color here. And I don't want the value 0 to be colorful because that's no water. So if I click on that 0 value and that color of the 0 value, I can put the opacity to 0%. And just like that, I apply it. I removed the 0 value from being visualized. And now I might present to you a pretty nice plugin. You might need to install it, but that's quite fast in QGIS. On the top, if you go to plugins, manage and install plugins, you can search for quick map services. So I know everything is quite fast, but this session is recorded anyway, so you can always rewatch it. So the plugin is called Quick Map Services. You just install it. So again, plugins, manage and install plugins, and then you search the Quick Map Services. After the installation, you can find them in your web section. So in web, you see Quick Map Services. You might not see as much as I do, and that's because you need to adapt some settings. So you go to Settings, and then you go to the tab More Services, and you click Get Contributed Pack. Now, last version of Contributed Pack was downloaded. Thank you, save. And now if I go to Web and open Quick Map Services, I see QGIS, AutoNavi, Bing, Esri, GeoQ, Google, Mapbox, NASA, Car2DB, Basemap, USGS, and so on, and the OpenStreetMap as well. So let's just go with Google Satellite. And you can now see how that my zero value is not there anymore, because if I zoom into my river, I see just the water, the detected water in the color blue, and the satellite imagery. And I see, for example, here there is like a side arm of the river that is mostly dry, or you see river banks that should be mostly dry, but of course in rainy season they're flooded as well. Now, of course, this background image is not from the same day. So of course you can do the same process as we did before with Sentinel-2 instead of Sentinel-1, or you even use the Dunia streamer. We saw that yesterday. You go to Dunia, streaming. I don't know why I'm not signed in. And then select the tile and download a normalized difference water index or a normalized different moisture index, and just upload it into your sandbox. You can then reuse it. And if you color it a bit more beautiful, as I did, you can compare the moisture index from someone after with the flood itself. So you see, okay, prior to the flood event, there was no water here, but with the flood, there was actually water in this old river arm as well. And also some parts outside of the river are still flooded, especially these dry river banks. Of course, this is not a huge flooding event. There is a better example. Unfortunately, for this event, there was just radar data available for a day shortly before it was really crazily flooded. So it is a bit more flooded, as you can see, but not as much as this flood event actually did. But for this example, it is more than sufficient because it shows you how you can use Sentinel-2 data to detect water and also wetness. So, of course, there are options to make the results better, and to detect wetland areas also, besides just water areas. As I showed you, you might want to use multi-temporal SAR metrics, so using more than one day instead of a single date. The process of pre-processing is basically the same. There might be one or two other tasks that you might want to do, like applying the orbit file, to really having a pretty nice pre-processed Sentinel-1 imagery. On top of that, you might want to compare it and combine it with Sentinel-2 optical imagery that needs to be pre-processed as well, using cloud masks, using atmospheric correction, and so on. And then, of course, you take the polarization ratio that, for example, Cornelia explained, and create some change metrics. So with indices provided by Sentinel-2 imagery combined with processed Sentinel-1 data, you can do pretty good classifications with supervised or unsupervised classification methods. If you want to go deeper into machine learning, of course, you can then use a normalized difference water or moisture index from Sentinel-2 in combination with the VV polarized pre-processed Sentinel-1 imagery, put it into a random forest model, and get pretty nice results for not just water bodies, but also wetlands like marshes or just wet fields. So even in that regards, multi-temporal data is pretty important because you get wet areas when they're just wet for a few days, like if you irrigated a field, or if they're really extremely wet, like in swamps and marshes. And with that, also my example using SNAP and QGIS for the more GIS-oriented guys of you is finished. I hope you liked it. And for more explanations, I will also share you this link. It is basically the one that I used for this pretty nice SNAP example. It might give you a bit more background on why to choose that polarization, which although already Cornelia explained, and other explanations. And you will find, of course, similar tools and samples everywhere out there if you Google it. So and they will all point you towards SNAP and of course GIS in case you don't want to code it yourself.
Okay, thank you, Johannes and Cornelia, for those informative sessions. We've learned so much. We are grateful that you took your time to teach us all this. And I can't see any questions in the chat. Maybe if someone has a question, kindly raise your hand so that we can unmute you. Hi, Johannes, you are muted.
Sorry. I see there was one question. I tried opening Dunia platform, but ask name and password. So yes, you need to register before you can sign in. We had that yesterday. So if you go to Dunia, you click sign up on the top right corner. You provide your email address, your name, your password. You get a confirmation mail, and after that, you can use your username and your password. All that is for free. So after that registration process, you can log in and you can use this Dunia sandbox. If you have missed yesterday's session, as Grace said, and as we heard this question for a few times now, both sessions are being recorded and will be shared to all participants, I guess, right?
Yes, that's the case.
Exactly.
Yeah. So anyone with a
Sorry,
question?
Grace, did you ask a question before? I might not have understood it.
No, I didn't have
Okay.
a question. I was just saying if someone has a question, they can raise their hand. Any question, comments, answers, anything?
If you have a question later today or some other day, feel free to use the support email or our email and write us. And then, of course, we can always answer your questions later on as well. And for those of you who have a question but are maybe shy to ask it, there are no stupid questions. So this topic is not too easy. Sentinel-1 data, especially the pre-processing process, has quite a few steps. So, but all of them are well documented. So in case you're interested, there are a lot of good sources to read why you should do a specific pre-processing step.
Thank you, Johannes. I think we can close it at that.
Okay.
Thank you everyone for for joining us. Thank you, Johannes and the team. We are very grateful. We've learned so much on my end, I can say that. And thank you so much. I think we can close it there.
Great. Thank you so much.
Bye.
Bye.
Bye.